Hello and welcome to this lesson on revenue analysis and data preprocessing. In this lesson, we'll be focusing on analyzing the revenue information from the cleaned and optimized GStore dataset. We'll also preprocess the data to make it ready for data modeling. The goal of this lesson is to understand how the target column, which is the revenue, correlates with the feature columns and what kind of preprocessing steps are generally required before modeling the data using machine learning. So let us start this lesson by importing the necessary libraries. We're importing pandas as PD to work with data frames. We're importing NumPy as NP to work with mathematical functions. We're importing Matplotlib's PyPlot module as PLT in order to create data visualizations. We're also importing Seaborn as SNS to work with data visualizations. And we're finally importing sklearn's preprocessing module in order to preprocess our data. And we're using the Matplotlib inline magic command to show the plots onto the Jupyter notebook. So I'll run all of these lines of code to make the imports happen. Great. Next, let's import the CSV file called clean_gstore_data.csv, which contains the clean information about each user's website visit along with the revenue they generated for Google. So I'm using the read_csv method from the pandas library, and I'm specifying the file path as data/cleaned_gstore_data.csv, and I'm setting the low memory parameter as false. Then, once the CSV file has been read in as a data frame, I'm assigning it to a variable called store_df. So let me run this line of code and make the assignment happen. Now, we can look at the first 5 rows of the data frame by calling the head method off of it. So I'll run this and we have our cleaned GStore dataset. We can also check the shape of the data frame by calling the shape property off of the data frame. So I'll run this and we have 900,000 different rows with 31 different columns. Okay, now let us start the analysis by looking at how much percentage of the customers are actually generating revenue for the GStore. Since a single customer can have multiple rows of revenue information in the dataset tied up with the session history, let us group our data based on the full visitor ID and then sum the revenue. So here we're grouping the data frame, which is store_df, with the column name as full visitor ID. Then we're finding the sum of the transaction revenue for each customer. Finally, we're resetting the index and we're storing the entire data frame that is generated from this operation into the variable rev_df. I'll run this line of code. Now let's print the data frame. So I'll run this and here we have our data frame. And as you can see, we have full visitor ID over here and we have the total transaction revenue for each of these user IDs. We can select the customers who are generating positive revenue, that is revenue greater than 0, from this data frame. So for this, I'm selecting a condition over here where we're trying to get the data frame's value where totals.transaction revenue is greater than 0.0. And once this has been returned, we're resetting the index and we're dropping it. So I'm also assigning it to the variable positive rev_df. And if we look at the first 5 rows using the head method from the data frame, we can see our new data frame. And right now we have all of the values greater than 0 in this positive rev_df data frame. Also, let us check out the shape of this data frame. So I'll run this and we have about 9,996 different customers who are actually generating positive revenue for GStore. So we can quickly check out the percentage of the customers generating revenue, and for this we can divide this number, which is the number of positive revenue rows in this data frame, and the number of all rows in the data frame we saw earlier, and we're multiplying it by 100 in order to get a percentage. So only 1.39% of the users are actually generating revenue for the store. This means that the revenue data is highly imbalanced and there are way more non-revenue generating users in the dataset than revenue generating customers. Next, let us look at the distribution of the revenue information in the dataset using statistical and graphical methods. So here I'm printing out some of the statistics of our data. I'm finding the mean, the median and the max value of the positive rev_df's transaction revenue. So as you can remember, positive rev DF is the data frame containing all of the customers with positive revenue. So if I print out all of these lines of code, we can see that the least revenue a customer has generated in total for GStore is 10,000, then the max value is quite much. But you can also notice that the mean and the median are quite different, and this means that the data is skewed. So let's see how much the data is skewed by using a graphical representation of this distribution. So we have the code for making the plot over here, and I'll just run all of these lines of code and we'll discuss what is happening. So as you can see, we have our plot over here, and if we look close, first I'm setting the x-axis value for the plot as the range of the positive rev DF's number of rows given by SIP, and we're selecting the first index, which is the number of rows. So when printing that out, we get a range from 0 to 9996. Then for the y-axis values, we're sorting the positive rev DF's total transaction revenue based on its values, which is the actual transactional revenues. And as you can see, the first value over here is 10,000, which is given by E plus 04. So 1, and then there are 4 zeros after that. So our y-axis values are the transactional revenue sums. So if we look at the plot over here, we can see that most of the revenue is at the 0 line over here. But there are some outliers, and we have some very high revenues over here. We can also plot a kernel density estimation plot, which will give us a proper idea about the skewness of the data. Skewness refers to the fact that there are cases where one or a few points are much larger than the bulk of the data, as we can see over here. So to do that, we're using the displot method from the SNS library, which is the Seaborn library, and we're passing in our column as the totals.transaction revenue. And we're setting the bins as 40 and the KDE parameter as true, since we want a kernel density estimation plot. And we're setting the title over here. So I'll run this line of code, and we can see our kernel density plot over here. And you can notice that most of the values are within this range, and there are some outliers over here, as we had seen in this plot as well. So now, in order to fix this skewness, we can take a common step, which is finding the logarithmic value of the data. We'll be using the log1p method for this, and we can later convert the logarithmic value to the original value using the expm1 method from NumPy. So I'll just give an example of what kind of changes we can see. So I'm calling the log1p method from the NumPy library, and I'm passing in the value 20, and this will give us the logarithmic value of 20 plus 1. Then we can get the original value back by just using the expm1 method and passing in our logarithmic value of 20 plus 1, which is given by this line of code over here. So if I run both of these lines of code, we can see that the logarithmic value of 20 plus 1 is this, and the original value is 20. Hope you understood that. Now let's do the same for the totals.transaction revenue. So for that, I'm calling the log1p method from the NumPy library, and I'm passing in the values of the total transaction revenue column. Then I'm replacing this value with our original column values by assigning it over here. So I'll run this, and this will get us the natural logarithm of 1 plus the input array in an element-wise manner. So again, let's plot a scatter plot. So we're calling the scatter method over here, and we're setting the x-axis values and the y-axis values as before. So if I run this, we have a logarithmic transactional revenue distribution. And as you can see, some of the values are going this way and some of the values are going this way, and we cannot make any assumptions from this plot to know how the data is distributed. So let us plot a KDE plot again, and this time you'll see a clear difference. So I'm using the displot method from the Seaborn library as before, and I'm using the column as totals.transaction revenue, bins as 40, KDE as true, and we're also keeping the title. So if I run this, we have our KDE plot, And the data now looks like it follows a normal distribution where the mean is actually equals to the median, and there is no large skewness in the data as we had seen before. So let us also change the value of the transaction revenue in the original dataset to a logarithmic range to remove data skewness. So I'm calling the log1p method from the NumPy library, and in the original data frame, which is store_df, I'm passing in the values of the transactional revenue column, and again I'm replacing it in the original data frame's revenue column. I'll run this line of code and the replacement has been done. So now let us check the correlation of all numeric columns with the revenue. For this, we can call the core method off of the data frame and we can select our revenue column. So I'll run this. So here you can see the correlation of different columns with the transaction revenue column, and none of the columns are highly correlated with the revenue information. However, totals.pageviews and totals.hits do have some visible correlation. So we have to make sure that we take the combination of multiple features in order to predict the revenue. For this, we can convert the categorical columns to numerical columns by label encoding them, and this is a data preprocessing step. Label encoding converts the values in the columns containing non-numeric values to values between 0 and the number of classes -1. So let's print a concise summary of the data frame by using the info method from the data frame. So I'll run this. And as you can see, there are a lot of object columns over here. So we can convert these object columns into strings and then label encode them. So for that, I'm creating a list of all of the categorical columns, which is the object columns over here. And I'll run this to initialize the list as cat_calls. Okay, now we can run a for loop across this list, which is cat_calls, and one by one, we can label encode all of these data columns. So first, I'm initializing the label encoder in each for loop. Then I'm label encoding the categorical column by calling the fit_transform method from the label encoder we have initialized over here. Then I'm passing in the store_df and the column, which is the column name in the list. And we're converting this column into a string and we're fetching its values. Then we're replacing the label encoded column with the original data frame's column values. And in this way, we're actually converting the categorical columns into label encoded columns. So if I run this, all of the categorical columns have been label encoded. So let us look at the first 5 rows using the head method of the store_df data frame. And now you can see that instead of object data type values, we have actual numerical values in all of the columns. And now we can again check the correlation of all numerical columns with the revenue. So again, I'm calling the curve method from the store_df data frame and we're selecting the totals.transaction revenue column. So I'll run this. And now we have the correlation of all of the columns in our data frame. And still, we can see that only totals.pageviews and totals.hits have some visible correlation with our target variable, but others are quite low. So now we have a lot of columns that are somewhat correlated with the revenue information. The data is now ready for applying machine learning on it. By the way, we haven't performed feature scaling in this dataset to convert all numerical values within a certain range, that is 0 to 1 or -1 to 1 and so on. This is because we will be using a tree-based algorithm for data modeling, and in such algorithms, feature scaling is not required since the result will not be affected. So finally, let us save this data frame in a CSV file to use in the next lesson of this course. So I'm exporting the data frame using the to_csv method and I'm passing in the file path as data/preprocess_gstore_data.csv, which is the file name. And I'm setting the parameters header equals to true and index equals to false. So I'll run this line of code and let's export the data frame as a CSV file. So that is it for this lesson. As an exercise, I would encourage you to preprocess the data even further by removing columns that have almost zero correlation with the revenue information. Doing so may help you get more accurate predictions when applying machine learning to predict the revenue in the next lesson.